Welcome. Today, we're going to start doing multivariate calculus tutorials, but our first one is on basic one variable calculus. But this will be part of a series. And so if you're interested in that, then stay tuned. I've already got a series of lectures on this topic, so be sure to find those. All right, so let's get started. Now, our first problem asks us to fill in the following table, the missing entries in the following table of integrals and derivatives, but you'll notice they're just one variable function. So let's begin with the top row. Find the derivative of 2x squared plus 4. Okay, so the derivative of 2x squared is 2 times 2 times x, and then plus 0. So if I copy this out, this is the function, then the derivative in this column, so the derivative is 4x. Okay, now the antiderivative, let's just call this integral of 2x squared plus 4. What we do here, we add 1 to the exponent, we get 3, we divide by our new exponent. Because this is a polynomial, so we have 2 over 3x cubed, and then plus 4x plus c. C is any constant. Okay, so let's move on now to the second row. So we have the function x to the power of 1/3. You see I've rewritten that there to make it easier to see how we differentiate and integrate this. So differentiating this, we have x to the power of p. P is a real number, so we bring that p down, and we subtract 1 from the exponent. So 1/3 minus 1 is minus 2/3. Okay, so that's our derivative there. Next, integrating this, we add 1 to that exponent, 1/3. We get 1/3 plus 1 is 4/3. So x to the power of 4/3. We divide by the new exponent. Now dividing 1 divided by 4/3 is 3/4. 3/4 x to the power of 4/3 plus c. Okay, let's draw another line for a new row. And let's move on to sine of x. All right, now you should just remember that the derivative of sine of x is cos of x. Now going the other way, the integral of sine of x is minus cos of x, because the derivative of cos of x with respect to x is minus sine of x. So minus gives us sine of x. Okay, so this is the integral, but we need plus c. Okay, next one. We are given an antiderivative, sine of x plus c, of a function f, and we're asked to find the original function. So to do that, we need to differentiate this. So the derivative of sine of x with respect to x is cos of x, and the derivative of c is 0. So we just have cos of x there. Now, the derivative of this function is the derivative of cos of x, which is minus sine of x. Okay, there we go. Now, next, we have tan of x. Okay, now the derivative of tan of x, you can just remember that that is sec squared if you like, and fill that in there. But let's just fill in the details here, because if we have y equals tan x, then that's sine of x over cos of x. And to find the derivative, what we need to do is use the quotient rule. So dy on dx, or y dash, is 1 on that denominator v squared, 1 on cos squared. And then in brackets here, we have v du on dx, cos x times the derivative of sine, which is cos of x, and then minus the other way around. So u, which is our numerator, times the derivative of the denominator, which is the derivative of cos of x, which is minus sine of x. So let's put that in brackets. Okay, and then we have two minuses, so that makes a plus. So what we have then is 1 on cos squared x, in brackets, cos squared x plus sine squared x. And of course, a trig identity says that this numerator there is 1. So we have 1 on cos squared x, which is sec squared x. Okay, so we come up here and we write sec squared x. Okay, now going the other way, how do we integrate tan of x with respect to x? Well, let's call this sine over cos again. Okay, now notice that there is a relationship between the numerator and the denominator. So if we differentiate cos of x, we get minus sine of x. So what we can do here is introduce a minus sign, put in minus sine x there, so that two minuses multiply together to give us plus sine. So we have this, and now notice that the derivative of the denominator is the numerator there in this part of it, and so we're going to get the natural log of the denominator. But how does this work? It happens through substitution by saying let u be equal to cos of x. And then what we do is differentiate cos with respect to x. So du on dx is minus sine of x. And then this tells us how to make a substitution up in here so that we can replace treating this as a fraction, although it's not. Okay, so we have that we can replace dx with du over minus sine x in here via substitution. So let's do that now. We have minus the integral of minus sine x. We are replacing dx with du on minus sine x. And so you can see that those nicely cancel. And then this is over cos of x, okay, which is our u. So we have, and I need another piece of paper here. So then when we simplify this, we have minus the integral of, canceling the minus sine x, 1 on u du. Now this integral is easy. It's the natural log of u. So we have minus natural log of u plus c. Now remember, u is cos of x, so this is minus natural log of cos of x and then plus c. Okay, so let's go ahead and fill this in our table and make a new row. So this now is our second last row. So here we're given that y dash is e to the x. So to get the original function there, we need to integrate e to the x. And so since the derivative of e to the x is e to the x, the integral of e to the x is e to the x, but we just need to add constant of integration. So e to the x c. Okay, now to find the antiderivative or integral of this function, the integral of e to the x is e to the x, the integral of c is c times x, and then we need a new constant. So let's rename this c1, because when we integrate this, we're going to need a c2. So we have e to the x c1 times x plus c2. Okay, let's make a new row and finish off our table. So in the last row, we have the natural log, so I'm going to write ln here, of t plus 1, where t is positive. Okay, so we need to differentiate here natural log of t plus 1 with respect to t to find the function. So the derivative of natural log of t with respect to t is 1 on t, and the derivative of 1 with respect to t is 0. We have 1 on t there. Now we can also write this as t to the minus 1, and that probably helps in reminding us what the derivative of that is. So when we differentiate this, we bring the minus 1 down, we subtract 1 from the exponent, so we have minus t to the minus 2, and we can express this as minus 1 on t squared. Okay, so we've now completed that table. So let's move on now to question 2. Okay, so question 2 says use the rules of differentiation to calculate the derivatives of the following functions and then simplify where possible. Okay, so our first question asks us to differentiate 2x times x squared plus x. So we can do this in two ways. We can use the product rule, or we can expand and then differentiate. The latter one seems a bit better. So let's expand this first. We have 2x to the power of 3, 2x squared. Okay, and so let's differentiate this. So y dash is 2 times 3, x to the power of 3 minus 1 plus 2 times 2, x to the power of 2 minus 1. Okay, so simplifying this, we have 6 x squared plus 4 x to the power of 1. All right, now let's do this as well using the product. So we have y is equal to 2x times x squared plus x. Now let's call this first one u, and let's call this v. So the product rule says y dash is v du on dx plus u dv on dx. Okay, and so we have x squared plus x, that's our v, times the derivative with respect to x of 2x, and then plus the other way around. So we have 2x times the derivative with respect to x of v, which is x squared plus x. All right, and so now we need to differentiate each of these and simplify. So the derivative of 2x with respect to x is just 2. So we have 2 outside of x squared plus x. Then over here we have 2x times the derivative of x squared plus x with respect. So that's 2x plus 1. Okay, so now to make it look like this line, we would want to expand this and collect like terms. So we have 2x squared plus 2x plus 4x squared plus 2x. Okay, so we've expanded. Now let's collect like terms. So 2 plus 4 is 6. And I can see that up here, that's not a power of 6, is it? That's a power of 2. It's right over the top of that. That should be 6x squared. Okay, not too bad. So 4 plus 2 is 6, x squared, and then 2 plus 2 is 4. So we get the same thing there. All right, so that was part A. Let's move on to part B. So here we've got f of x is sine of x over x squared plus 4x plus 2. So now for this, we're going to use the quotient rule to differentiate this. So let's call the numerator u and the denominator v. Okay, so f dash of x is 1 on v squared brackets v du on dx minus u dv on dx. So I tend to like to rewrite 1 on v squared for a while because v tends to be a bit big to keep rewriting. Did you hear that? To keep rewriting. Okay. I don't want to keep rewriting that. So I'll just fill that in at the end. And so here I can do the same thing with this. Now du on dx is the derivative of sine of x. And then we have minus sine of x times the derivative of that polynomial x squared plus 4x plus 2. Okay, there we go. So let's simplify this one. Again, let's write 1 on square until we get to the last line. Okay, now v is that polynomial, the derivative of sine is cos, and then the derivative of x squared plus 4x plus 2 is 2x plus 4. So minus, let's put the polynomial in front, 2x plus 4, and then we have sine of x. Okay, so now let's fill in our last line, this denominator squared. So I'll put it over one fraction bar or vinculum as it's called. So x squared plus 4x 2 squared. Okay, and then in our numerator, these are not like terms, so let's keep those as is. So x squared plus 4x 2 cos of x, and then minus 2x plus 4 times sine of x. Okay, there we go. And there's f dash. Okay, let's move on to part C. We have f of x is e to the 2x plus cos of 2x. Okay, so to differentiate this, we're going to need the chain rule. But first notice that the derivative of the sum is the sum of the derivative. So if we differentiate each one and then add the result, that'll be fine. All right, so let's let u be equal to 2x. Okay, and that's good in both cases. That'll be fine. So then du on dx is just 2. Now, to differentiate e to the 2x, well, we've called 2x u, so we have d on dx of e to the u, but now using the chain rule, we want to differentiate this in terms of u, so the chain rule would say that this is d e to the u with respect to u times du on dx. Now, we've already calculated du on dx, it's 2, but the derivative of e to the u with respect to u is e to the u. So we have e to the u and then times 2. Now u is 2x, so we can write this as 2e to the 2x. Okay, now doing the same thing with cos of x, the derivative of 2x using the chain rule. So this is the derivative of cos of u, du, and then du on dx. Okay, now the derivative of cos of u with respect to u is minus sine of u. Minus sine of u, and then du on dx, because we have the same u here, we know that that's just 2 because we've already calculated. Okay, now let's pull that 2 in front after the minus sign. We have minus 2 sine of u, but u is 2x. All right, and so now we can add the two of these together to get the derivative of f of x, which let's just call that f dash of x. So f dash of x is 2e to the 2x minus 2 sine of 2x, and it's possible to factorize a 2 out of this. So you could, if you wanted to, call this 2 outside of e to the 2x minus sine of 2x. And that's just fine. Okay, let's move on to 2 part D. So in 2 part D, we have y equals x to the 4th plus x cubed all to the power of 2. Now it's clear we need to use the chain rule here. We could expand this and then differentiate, but let's use the chain rule here. So let u be equal to the inside function x to the 4th plus x cubed. Okay, we know we're going to need du on dx in the chain rule. So du on dx is 4x cubed plus 3x squared. All right, so down to here, dy on dx is the derivative with respect to x of u to the power of 2, because we let this inside function be u, so that's u squared. Okay, now we want to express this as a derivative of u squared with respect to u using the chain rule times du on dx. Okay, so we have used the chain rule. Now let's differentiate u squared with respect to u. We get 2u. The u on dx we already know is this. Just fill that in. 4x cubed plus 3x squared. Now we let u be x to the fourth plus x cubed. So this is 2x to the fourth plus x cubed times 4x cubed plus 3x squared. And we're done with part 2d. So let's move on now to 2e. Okay, in 2e we have y equals the square root of t over e squared. Now, presumably, we're differentiating this with respect to t. So we want to write y as a function of t is equal to 1 on e squared. Now, 1 on e squared is a constant, and then we have times t to the power of 1/2. Okay, so y dash of t is dy on dt, which is, since this is just a constant, we can let that float through the operator. And so we have 1 on e squared d on dt of t to the power of 1/2. Okay, and so this is t to the power of p, where p is 1/2, and so the rules say that we pull down the 1/2 and subtract 1 from that exponent. Okay, now let's simplify. 1/2 minus 1 is minus 1/2. So we have 1 on 2e squared t to the power of minus 1/2. And it would be fine, in my opinion, to leave the derivative just like this. Okay, but we can simplify this a little bit further in expressing it in a similar way to what we were given to start with. So this is 1 over 2e squared square root of t, because that minus can come down into the denominator, but when we do that, we change the sign so that it's t to the 1/2 in the denominator, but t to the 1/2 is square root of t. Okay, so there we go. Okay, question 3, we are doing some fairly elementary definite integrals. So let's start with part A. Calculate the definite integral of x squared plus 3 between 2 and 5. So this is an area under a curve between x equals 2 and x equals 5, provided all of this is above the x-axis, which it is. Okay, and so here we have integrating x squared gives 1/3 x cubed. Integrating 3 is 3x. And then our brackets go around this. I usually like to choose square brackets. Some people just write a vertical line on the right-hand side. That's fine. So then we include our endpoints. Okay, now we need to sub in the 5 and sub in the 2 and subtract. So this is 1/3 of 5 to the power of 3 plus 3 times 5. And then we subtract, same function, but this time we sub in 2 there. So 1/3, 2 to the power of 3 plus 3 times 2. Now we want to simplify these and take that difference. So 5 cubed is 125. So 125 over 3. 3 times 5 is 15. But if we multiply 15 by 3, we get 45, so that we can put that over 3 if we want to. All right, now over here we've got 8 over 3, and then we have 6, but 6 times 3 is 18 over 3. So we have 125 plus 45 minus 8 minus 18, and this is all over 3. Okay, so 125 plus 45 is 130 plus 40, which is 170. So 170. And then over here, we have the sum of 8 and 18 is 26. So minus 26. And then that's all over 3. 70 minus 26 is, so 144 over 3. Then if this is 12 times 12, 12 over 3 is 4. So that's 4 times 12, which is 48. Well, now let's move on to part B, where we're calculating the definite integral from 0 to 2 pi of sine of x plus x. Okay, so we need to integrate this first. So the integral of sine of x with respect to x is minus cos of x. The integral of x is 1/2 squared, 0 to 2 pi. All right, now we sub in 2 pi, put a bracket around this, subtract leave a fair bit of space here. So minus cos of 0 plus a half 0 squared. Okay, simplifying this, cos starts up at 1 and it's periodic of period 2 pi. So this is minus 1 here because we have a minus in front. So minus 1 plus pi squared on 2. And then over here we have minus 1 plus 0. So minus minus 1 is plus 1. Hang on, I can see that I've made a little mistake here. So that should be 2 pi all squared. Okay, so in here that's 4 pi squared on 2. And so now we can see that the 1's vanish and we have 2 pi squared. Question 3, part C. Integrating e to the power of t plus 1 with respect to t from 1 to e. Okay, so the integral of e to the t with respect to t is e to the t. The integral of 1 with respect to t is t. Put square brackets around this. Repeat the 1 and the e. All right, so now we substitute in t equals e. So then we have e to the e plus e. Subtract, sub in 1 here. So e to the 1 plus 1. And so we have e to the e plus e minus 1. So the two e's vanish and we have e to the e minus 1. Okay, part D. Minus 1 to 1, and we are integrating x squared with respect to x. Okay, so let's integrate this first. We have 1/3 x cubed minus 1, 1. Okay, subbing in a 1, we have 1/3, 1 to the power of 3, and then we subtract 1/3 minus 1 to the power of 3. So notice we're taking a little bit of care with this. Now, minus 1 cubed is minus 1. There are two minuses, so we'll get a plus out of this. So we have 1/3 times 1 is 1. 1/3 there. And then plus another 1/3. So we have 2/3. Okay, part E. A definite integral, 1 on x between 1 and infinite. Okay, so first let's integrate x to the minus 1. So if we were to add 1 to the exponent, we would get 0. So this is the exceptional case. So we have the natural log of x for that. Okay, so we write it in this way. Now, we need to use a limit for this. So we'll express this as the limit as a goes to infinite of the natural log of a, and then we subtract the natural log of 1. Okay, so now natural log of a is that a goes to infinite. This diverges, so there's no upper limit on this. So this would be infinite and minus 0. We'll just say that this diverges so that this integral does not exist. Okay, question 4. Make a quick sketch of the following function. So for a, we have f of x is x squared plus 2. So to sketch this one, well, when x is 0, we have 2. So 1, 2. So let's put a point there. And then when x is 1, we have 2 plus 1 squared is 3. So we have a point here. When x is 2, we have 4 plus 2 is 6. We have a point here. And so this, of course, is a parabola. It keeps going up like that, and it's symmetric about the y-axis. On the other side, it looks like the mirror image of that. Okay, so there's a quick sketch of that. Now, let's move on to 4b. So in 4b, we're asked to sketch y equals sine of t minus 1. Let's put t there and y up here. Let's mark some key points. So 2 pi, pi on 2, 3 pi on 2. Okay, and then up here, let's put 1 and minus 1 and then minus 2. Okay, now if we were plotting sine, so if I were plotting sine, we would top out there pi on 2, at 1, and then we would meet the axis again at pi, and then at 3 pi on 2, we'd be at -1, and then back to 2 pi. But this is sine of t minus 1, so we've got to shift all of these down 1 unit. So we start here at -1, we come up to 0, and then we're back at -1 when t is pi. And then shift this down 1 unit down to -2. And then at 2 pi, we're back here at -1. Okay, and so now we just need to fill in a curve or a sine wave. Okay, so there's my quick sketch, but let me give you a Mathematica sketch of this also. Sine of t, and then subtract 1. And then let's do this as t goes from 0 to 2 pi. Okay, so there we have a Mathematica sketch of that. All right, now moving on to 4 part C. So y equals 2 e to the x. Now again, let's pick a couple of points. So when x is 0, we have e to the 0 is 1, so 2 times 1 is 2. So 0, 2. Okay, when x is 1, e to the 1 is e, so we have 2e. And then when x is 2, we have 2 times e squared, so 2e squared, and so on. All right, so to make a quick sketch of this, we have when x is 0, we have 1, 2, so we have a point here. When x is 1, we have 2e. Now e is 2.71828, and so on. So twice that will be a little bit more than 5. Okay, so here. And so this should look like an exponential curve. So as e goes to minus infinite, in other words, the limit as x goes to minus infinite, we would have 2 over a very large number, so 0. So we have a horizontal asymptote here on the x-axis. And then this goes up very dramatically. Okay, so now let's do a Mathematica sketch of this function. So we have 2, and I'll just write exp because it's easier to type. Go from, say, -5, 5. Okay, and so there you see we have something a lot like what I've sketched there. Okay, so in question 5, we are just evaluating multivariate functions at particular points. So here we have z as a function of x and y is equal to x squared plus 3y squared. And we want to evaluate this at 2, 3. So what we're doing then is replacing the x with 2 and the y with 3 and asking what is the result of this. So it's 2 squared plus 3 times 3 squared. So for this we have 4 plus 3 times 9, which is 27. So 4 plus 27 is 31. All right. Now, question 5b. So same thing, different function and different point. So z is a function of x and y, and this is x sine of y plus y cos of x, and we're evaluating this at the point 0, 1. So z of 0, 1 is 0 times sine of 1 plus 1 times cos of 0. And so this is 0 plus 1 times 1 is 1. And so we get 1. All right, let's move on to question 5c. So we have z is a function of x and y, or z if you're in the USA. 3e to the x times y. X is 2 and y is pi. So we are evaluating z of 2 comma pi. So that's 3e to the power of 2 pi. And we'll just leave it like that. Otherwise, we simplify this as a decimal expansion. Okay, but let's leave it. All right, question 6. Consider the piecewise function x squared plus 3x plus 1 if x is greater or equal to 0 and it's 1 minus x otherwise. So if x is less than 0. So show that f of x is continuous but not differentiable. Okay, so what we need to do is evaluate the limit as x goes to 0. Now, why I choose 0 is because this function right here is continuous, and this function is continuous because they're both polynomials. So potentially, things could go wrong at 0. So what we're going to do is look at the limit on the left, or from below as it's called. So I put a 0 superscript minus 1 of f of x. So this is to the left of 0 on the number line. And so what we're doing then is, since it's on the left, we're looking at this. So that's the limit as x goes to 0 of 1 minus x. Because on the left of 0, this is how that function is defined. Okay, and so this limit is 1 minus 0, which is 1. Now, the limit as x approaches 0 from above, or on the right-hand side of 0. Now, on the right-hand side of 0, the function is governed by this. So we have the limit as x approaches 0, x squared plus 3x plus 1. And so now substituting in 0, we have 0 squared plus 3 times 0 plus 1, which of course is just 1. Okay, now these two limits are both 1. They agree. So since the limits agree, the limit as x approaches 0 of f of x exists and is equal to 1, because these are both 1 and they agree. They're equal. So the limit at 0, or as x approaches 0 of f of x exists and it's equal to 1. All right, so now to show that f is continuous at 0, we have to show that the limit as x approaches 0 of f of x is equal to f of 0. So since f of 0 is equal to, now notice that this is a greater or equal to sign, and so f of 0 is defined. It's defined to be this function at 0. So we have 0 squared plus 3 times 0 plus 1, which is 1. F of 0 is equal to the limit as x approaches 0 of f of x. So f of x is continuous at x equal to 0. And then finally, we'll remark that since f of x is continuous for all a not equal to 0, where a is a real number, so a is an element of the set of real numbers, and f of x is continuous at x equal to 0, we must have f of x is continuous for all real numbers. So for all x in the set of real numbers. All right, so we've shown that it's continuous, but now we need to say or show that it's not differentiable. So let's say for x greater or equal to 0, f dash of x is the derivative of x squared plus 3x plus 1. So we would have 2x squared plus 3. Okay. Now for x less than 0, we have f dash of x is the derivative of 1 minus x, which is just 1. Or sorry, minus 1. Okay, now so what we need to do here is show that these two don't match up at 0. So the limit as x goes to 0 from below of f dash of x, this is the limit as x goes to 0 of where that's governed. So this one, and so we have minus 1 for that. Now on the other side, the limit as x goes to 0 from above of f dash of x, so we have the limit as x goes to 0 of 2x squared plus 3. So this is just 3. And so notice that 3 is not equal to minus 1. So the limit as x goes to 0 of f dash of x does not exist. Okay, and so we say then that f is not differentiable at x equals 0. So f of x is not differentiable at x equal to 0. And so f of x is not differentiable on the set of real numbers. Okay, so what we've learned then in question 6 is that this function is continuous, but it's not differentiable. So let's go ahead and give a Mathematica plot of this function. So I need to put in a conditional. So if x is greater or equal to 0, then we have x squared plus 3x plus 1, and otherwise we have 1 minus x. So I can just take this conditional and plot that conditional. X goes from, say, minus 3 to 3. All right, so let's have a look at this. So you can see it's continuous. In other words, we don't need to lift up our pen when we sketch this, but at x equals 0, there is a sharp point. You can see that right there. There's a sharp point, meaning on the left, the derivative is one thing. On the right, the derivative is another thing. So the derivative is not continuous at 0. So let's also plot the derivative. So I've got to differentiate this here, and I'll just do that manually. Okay, so here is a plot of the derivative of that function, and you can see that the derivative is not continuous. Therefore, the function f of x is not differentiable at x equals 0, and hence it's not differentiable on the set of real numbers. Question 7. So we've got a function from 2 space to 1 space given by f of xy is a piecewise function. It's x y squared over x squared plus y to the 4th if x and y are not both 0, and it's 0 otherwise. Okay, and so we're asked to show that f is not continuous. So the hint says the limit as x, y approaches 0, 0 does not exist. If the limit exists, then it must be the same along every path towards the point 0, 0. So we've got to show that along 2 different paths, y equals 0 and along y squared equals x, we do not get the same limit. All right, so I first want to begin by showing you a 3-dimensional plot of this function. So let's open up Mathematica, and I'll write plot 3D, and I'll just plot xy squared over x squared plus y to the 4th. Okay, and so there it is. Now I will grab it and show you that it possibly looks like along 2 different paths, this ends up in a different place. Okay, so if you come along y equals 0, you end up in one place, but along another path, these don't match up. And it's really hard to see, but you can see it's like a sheet that has been pinched. So Mathematica struggles to show you exactly what's going on here because there's so much dramatic change near 0.00. Let me also plot the two paths. So I'm going to write contour plot 3D, and then I'll take these, paste them in there, and then I'll take a Z range as well. Okay, and so let's call this one A, let's call this one B, and then let's display the two of those together. All right, so here, y equals 0, we're just traveling along the surface on that plane towards 0, 0. Okay, and so you can see it looks like it might be something like 0 or 1 or some small number. Okay, so now the other path was y squared equals x. So let's include that here also. All right, so this is a curved path. Now that's in blue. You can see just little bits of it. So along this path, where do we end up? Okay, so we're going to show that these are not the same number. When you travel along that path on the surface, you don't have the same number. All right, so now let's go ahead and do the question, which is question 7. Okay, so C1 is the path y equals 0. Okay, so we'll say along C1, the limit as the point xy goes to 0, 0 is equal to the limit as x goes to 0. Now, since we are on y equals 0, what we can do here is replace all of the y's that we see in that function with 0. So that's x times 0 over x squared plus 0 to the 4th. Okay, and so we see that we have the limit as x goes to 0 of 0, because 0 over x squared is 0. Since x is not equal to 0 itself, we have 0 for that. And so that limit is just 0. So what that's saying, back to the picture here, is that along this path, the limit as xy goes to 0, 0 is 0. Okay, now let's do this along C2, y squared equals x. Okay, so along the path C2, the limit as xy goes to 0, 0, f of xy. Now, you know what? To distinguish these, I often put the path name above the arrow, so I would do that here also. Okay, so this is... Now, what we'll do first is we will take all of the y's there and replace... No, we'll take all of the x's and replace those with y squared. So we will have y squared times y squared over y squared squared plus y to the 4th. And this is the limit as y goes to 0. Okay, so let's simplify this. We've got the limit as y goes to 0 of y to the 4th over y to the 4th plus y to the 4th, which is 2y to the 4th. Now, in a limit, we can do a cancellation. And so we've got the limit as y goes to 0 of 1/2. And the reason why we can cancel in a limit like this is because we are looking at the value of this near y equals 0, not exactly equal to it. So near y equals 0, we have 1/2. So the limit is equal to 1/2. Okay, now in particular, 1/2 and 0 are not the same. So let's note this is not equal to 0. So the limit as xy goes to 0, 0 does not exist because it's two different things along two different paths, and it must be the same thing along every path towards that point of interest. In this case, it's 0, 0. Just another point of care. So when you choose your paths, you have to make sure that those paths go through that point of interest. So in this case, it's the point 0, 0. So 0, 0 is on this path, and 0, 0 is on this path, because 0 squared is 0. Okay? So if this instead were the point 1, 0, I would have to choose a path that passed through the point 1, 0. Okay, so that was question 7. Now let's move on to question 8, which is to repeat the same question, but this time replace f with this other function that we have right here. Okay, so let's begin with a plot of the function. So I'll just take all of this, copy it, we'll paste it down into another cell. Okay, so in the numerator we have a sum, so I'll put a bracket around that numerator. So 2x squared plus 2xy plus y squared. And then in the denominator we have 2x squared plus 3y squared. And then this time, let's choose the path C1 as y equals x, and let's choose the path C2 as y equals 2x. Okay, so here we have it. There's the surface, and then the blue is probably y equals 2x, and the y equals x, that'll be the vertical plane in yellow or orange. Okay, so let's try this first along C1, which is y equals x. So again, this is a piecewise function. So it's 1/3 if x and y is 0, 0. And it's given by this if xy is not the point 0, 0. Okay, so along C1, so the limit as xy goes to 0, 0 along C1 is, so we're just going to take this and replace this with, replace all of the y's with x. So 2x squared plus 2x times x plus x squared over 2x squared plus 3x squared. This is the limit as x approaches 0. Okay, so now we can collect like terms. So we've got 2x squared plus 2x squared is 4x squared plus another x squared is 5x squared. And then in the denominator, we also have 5x squared. So we've got the limit as x approaches 0 of 1, which is 1. All right, now along C2, so C2 is the path y equals 2x. So the limit as x, y goes to 0, 0 along C2 is the limit as x goes to 0. Now I'm just going to replace all of the y's that we see here with 2x. So we have 2x squared plus 2x times 2x plus 2x all squared, and then over 2x squared plus 3 by 2x all squared. Okay, so simplifying this, we have 2x squared plus 4x squared is 6x squared plus another 4x squared gives us 10x squared over 2x squared plus 3 times 4, 12x squared, so 14x squared. Okay, now canceling the x squared because we're just looking near x equals 0, but not at x equals 0. We have 10 over 14, which is 5 over 7. So we get a limit of 5 over 7. But notice this is not equal to 1, and 5 over 7 is not equal to 1/3. So this is certainly not continuous at the point 0, 0. Okay.